All right, welcome everyone. So everyone's online today, so please speak up, use the chat window, go ahead and press the raise your hand button whenever you have questions. All right, today we are talking about the normal distribution. And based on what we're talking about in class today, I recommend trying these 4 problems from homework 6. All right, so the normal distribution, also known as the Gaussian distribution, is a distribution that you've probably seen before. It has this classic bell-shaped curve. So this is the graph of its density function. And this curve has this formula for its PDF. So 1 over sigma times the square root of 2 pi times e raised to the power of negative y minus mu quantity squared over 2 sigma squared. So go ahead and take a moment to get that copied down. All right. And this holds for values of y, the random variable, between negative infinity and infinity, so any possible values. Mu represents the mean of the distribution, and that can also take any value between negative infinity and infinity. Sigma is the standard deviation that controls how spread out the bell-shaped curve is. So that needs to be greater than 0. All right. Some important facts about the normal distribution. First is expected value, and that is equal to the mean mu. So that makes sense. Mu is what we're calling the mean, and expected value is the long-term mean. And because the normal distribution is symmetric, it's also going to be centered at its expected value. So we talked yesterday about PDFs aren't necessarily centered at their means. Their means are sort of the center of mass, but that's not necessarily where the peak is. For a normal distribution, that is where the peak is. And the variance of y is sigma squared. So sigma is the standard deviation. And we can prove both of these using moment generating functions, which we'll see next week or the week after. One important normal distribution to be aware of is the standard normal distribution. So this refers to a normal distribution that has a mean of 0 and a standard deviation of 1. So here's what that looks like. All right, so if we want to use a normal distribution to compute the probability that y is between 2 values, say a and b, we can't actually do it by taking the antiderivative and then plugging in the endpoints. Because the antiderivative of the density function doesn't have a closed form. We can't write a formula for that antiderivative. So what we do instead is compute the integral of the density function from A to B numerically. So one way to do that is on a TI-83 or TI-84 calculator. Press the second key, and then you choose the VARS button, which gets you to distributions, and then choose normal CDF. And the arguments here are A, comma B, so lower bound and upper bound, comma mu, comma sigma, so mean and standard deviation. And if you do want just a one-sided probability, say the probability that y is greater than or equal to A, so no upper bound, no B, in that case you would use infinity for B, which you can put into your calculator as the approximation 10 to the 99th, just a very large number. If we were finding the probability that y is less than or equal to B, so no lower bound of A, then you'd want to use a lower bound of negative infinity, which you put in as negative 10 to the 99th. And an important idea here is that you don't want to put in 0 for the lower bound. Even if you're modeling something like people's heights that can't actually be negative, you still want to model it with a normal distribution where the area under the curve of the density function totals up to 1. And if you cut it off at 0, that doesn't work. So even if we're modeling something that technically can't be negative, we still use negative infinity, or negative 10 to the 99th, as our lower bound. The other approach is using R. You can use the p-norm function. So remember that p is our prefix to find the probability of being less than or equal to something. So p-norm of y comma mu comma sigma would give us the probability of y being less than or equal to little y, whatever number is the first argument here. Questions so far? So sigma and mu are, mu is the mean and sigma is the standard deviation. Other questions? All right. So let's try this. Heights of women in the US are approximately normally distributed, with mean 66 inches and standard deviation 2 inches. Try using either normal CDF on your calculator or p-norm in R to find the percentage of women that are shorter than 67.5 inches.
would you use 0 as the lower bound?
Good question. No, you're still going to use negative infinity or negative 10 to the 99th as the lower bound. Because like I said, we want to still have the total area under the normal curve be 1. So we don't want to cut it off at 0, even if, in this case, heights can't actually be negative. So in this case, 0 is pretty far from the mean.
Will it be 0.77333726?
Sorry, what?
Will it be 0.77333726?
Does that agree with what other people got?
Pardon?
Does that agree with what other people got? All right. So either one of these would work. Let's see, did I put in? Yes, so I got 0.7734.
Okay.
Excellent. In this case, the mean is 33 standard deviations away from 0. So in this case, you're probably going to get a really close answer, regardless of whether you use 0 or negative 10 to the 99th as your lower bound. But there are other situations where it would make more of a difference, and you would want to use 0 as, you would want to use negative 10 to the 99th, not 0 as your lower bound. All right. So if you are planning on taking the actuarial exam P, you're probably wondering, wait a minute, on that exam, I'm not going to be allowed to use R or a TI-83 calculator. What do I do? Well, the other way to compute probabilities from a normal distribution is using a normal probability table. So the first step in this is to convert your normally distributed random variable x to a standard normal random variable. And you do this by subtracting the mean and then dividing by the standard deviation. So this will shift and stretch or squish the normal distribution so that it's centered at 0 and has a standard deviation of 1. So it's a standard normal random variable. And z is usually used to represent a standard normal random variable. And then we use a normal probability table. So when you're doing this, be sure to check the table format and then look up the value of z and interpret it based on the table format, because some tables will give you probability of being less than or greater than or in between. So pay attention to what format the table is in. All right, so let's use this approach to solve this problem. So same setup, heights of women are approximately normally distributed with a mean of 66 inches and standard deviation of 2 inches. Let's use a table to find what percentage of women are shorter than 64 inches. So to do this, we want to start by converting our x variable that has a mean of 66 and standard deviation of 2 into a standard normal. So z is equal to 64 minus 66 divided by the standard deviation of 2. So we get negative 1. And then, oh, yeah, so, oops. So that means that whatever the probability of y or x being less than 64 is, it's the same as the probability of z being less than negative 1. So now we've changed the problem, so we're trying to find the probability that z is less than negative 1. So now, let's go to a normal probability table. So I've put on Canvas, in the general module, a normal probability table. This is what I got when I Googled actuarial exam P normal probability table. So I think that this is going to be the same format that you would see on actuarial exam P. So we start by understanding the table format. So here this is saying entries represent the area under the standardized normal distribution from -infinity to z. So in other words, the probability that z is less than z, little z. So that's good. That's what we want to find. We want the probability that z is less than -1. So now we would want to find -1 on this table by looking at the rows and the columns. And the way these are set up is that the units and tens place of z is denoting the row, and then the hundredths place is denoting the column. So we'd want to find -1.00 in this table. But there's a problem. If you notice, all of these numbers are positive. So these are telling us the probability that z is less than or equal to a bunch of positive values. So what can we do? Our table only has non-negative values of z. So we need to use the fact that the normal distribution is symmetric and say the probability that z is less than -1. So if we think about drawing a line at an x value of -1 here, the area to the left of that under the curve, that's going to be the same as if we drew a line at +1 and looked at the area to the right of that. So we want the probability that z is less than -1 because the normal distribution is symmetric, and specifically a standard normal distribution is symmetric around 0. Here we have, that's the same as the probability that z is greater than 1. So let's look at the table. So we're looking for 1.0 on the table, so that's this row here. And then we want the second place after the decimal to be also 0. So 1.00 gives us a probability of 0.8413. So 0.8413 is the probability that z is less than +1. Then we can use the complement rule to say that the probability that z is greater than 1 is equal to 1 minus the probability that z is less than 1. So we have 1 minus 0.8413, so we get 0.1587. So a little under 16% of women are shorter than 64 inches. Questions about this?
Nope.
All right. We can also compute quantiles. So this refers to computing a threshold on the x-axis that will give us a given probability. So for example, let's take our same example of heights. And say we want to fill in this blank. So 1% of women in the US are taller than what number? So here we're being given the percentage, or the probability, and we want to know the x value that's going to cut that off, make that threshold. So if you do this on your calculator, that's going to be using the inverse norm function, which is also in that table of distributions right under normal CDF. And what we're putting in here is, so 66 was our mean and 2 was our standard deviation. And the number that's coming first is the probability that we want to have to the left of our threshold. So if we want 1% of US women to be taller than this threshold, we would put in 0.99 as the probability of being shorter than that threshold. And to do this in R, it's the same, but our function is called Q norm. So remember, Q for quantile is giving us the threshold so that the probability of being less than that threshold is whatever our first argument is. All right. So now let's see how to do this same problem using a normal probability table. So in other words, we're looking for the value y, so that the probability that y is greater than y is 0.01. So in other words, the probability of being less than or equal to y is 1 minus that by the complement rule, so 0.99. So let's start by looking at our table. Now, we're not looking at the labels on the rows and columns. Now we're instead looking inside the table to find a probability that's as close as possible to 0.99. So here's 0.9901. And looking at the rows and columns, we have 2.3, and that's in the fourth column. So scrolling up, it's in the 0.03 column. So that means that we can get an area to the left of 0.9901 if we use 2.33 as our standard normal distribution quantile. So what this is saying is that to get 99% of the data to the left, we need to go 2 1/3 standard deviations to the right of the mean. And now we just need to find the x value or y value that corresponds to that. So take it out of a standard normal distribution and put it back into the normal distribution with a mean of 66 and standard deviation of 2. So we can use that same formula as we had before, z equals x minus mu over sigma, but we're just doing it in reverse. So 2.33 equals x minus 66 all over 2. So we get that y or x. I am messing with my variable names. Let's change this to y. So we get that y is 66 plus 2 standard deviations would be 4.66. So 70.66 inches. Questions about this? Folks online, any questions? Kailas, how did we find the correlation between y and z? Good question. So that is using our formula for the relationship between a standard normal random variable z and some other random variable that has a normal distribution with some other mean and standard deviation, which is this. And whenever you're working with the table, that's a standard normal distribution. So this 2.33 goes in the z position, and then we're solving for y or x. That's our random variable that has a normal distribution, but a mean of 66 and standard deviation of 2. Does that answer your question, Kyle? Okay, so how did we get the z equals 2.33? Yeah, so that was, we wanted to find the y value so that the probability that y is greater than y is 0.01, so that we can have this sentence be true, 1% of US women are taller than blank. Our probability table only gives us probabilities of being less than stuff, this particular probability table. So using the complement rule, we want the probability that y is less than or equal to y to be 0.99. So then on the table, we're looking for a number in the middle of the table that's as close as possible to 0.99. So 0.9901 here is as good as we can get. And that's in the row for 2.3 and in the column for 0.03. So if you concatenate the row and column labels there, we get 2.33. Cool. Any other questions about this part? All right. So some cool facts about normal distributions. One is that if y has a normal distribution with mean 0 and standard deviation sigma, then a times y plus b, where a and b are constants, also has a normal distribution with mean a times mu plus b and standard deviation absolute value of a times sigma. So we've seen this formula before for the mean and standard deviation of a linear function of a random variable. So this formula for the mean and standard deviation for a y plus b, that works for all random variables. But the part about the shape of the distribution, the type of the distribution staying the same, that is not true in general. It's true for normal random variables, and it's true for just a couple of other special types of distributions. So let's try using this idea. Customers at a grocery store pay amounts X that are normally distributed with a mean of $50 and standard deviation of $10. And after expenses, the store's profit is Y equals 0.4 times X minus 5. Try finding the probability that Y is greater than $20. So we know that Y is a linear function of X. So we know that Y is also going to have a normal distribution, because that's our special property of normal distributions. So then we want to find the expected value and standard deviation of Y. So its expected value is going to be 0.4 times the mean of X, so 0.4 times 50, minus 5. So we get 15 as the expected profit from a single random customer. And the standard deviation is the absolute value of 0.4 times the standard deviation of X. So 0.4 times 10 is 4. So then you want to be using normal CDF or p-norm or a normal probability table to find the probability that Y is greater than 20, given that it has a normal distribution with a mean of 15 and standard deviation of 4. So if you're using a calculator, you could use normal CDF of 20, 10 to the 99th, 15, 4 equals 0.1056. And in general, if you're doing this in your calculator or R, you should get the same answer. If you're using a normal probability table, your answer might be slightly different because of rounding, because the table only gives you 4 decimal places. All right. So now let's look at another way we can manipulate a normal distribution. Let's take the sum of a large number of independent random variables. So we're going to start with a bunch of random variables that all have the same distribution. That's not necessarily a normal distribution. So I'm going to do this using the clt.r. code that's on Canvas. So I'm starting with a vector called stored. Actually, let's make this a bunch of NAs. So we're creating a vector with 10,000 empty spots that we can fill with random values. And then I'm going to iterate 10,000 times. I'll generate one random number from a uniform distribution between 0 and 1. And I'm just going to store that. So take a minute to predict what this histogram is going to look like. All right, so here it is. Bars of roughly similar heights ranging between 0 and 1. So that should make sense. That's following the density curve of a uniform distribution is flat, and it's going to have a height of 1 so that we get equal probabilities of any range between 0 and 1, just depending on the width of the range. All right, so that was kind of boring. Now let's try it with taking the sum of 2 random numbers from a uniform distribution. So now, I had a -1 here to fill it with an impossible value, but I'm just replacing that with NA so that it's more clear that it's empty. So now we're generating 2 random numbers between 0 and 1. And then the thing that we're storing is going to be the sum of those 2 random numbers. Take a minute to predict to yourself what this distribution is going to look like. Is this going to look like a bunch of bars of approximately equal heights between 0 and 1?
Yes.
Let's see. Thumbs up or thumbs down, or if you're online, you can use the reaction buttons to say agree for yes, disagree for no. Is this histogram going to look like a bunch of bars of approximately equal heights? Sam, got a prediction?
Actually, it might be.
All right, so let's try this. Why does this graph make sense? Naya?
Presumably like more combinations where you can get a value 1, like 0.5 plus 0.5 or 0.949 plus 0.51. But 2 is harder to get because you need 2 high numbered values from the random numbers that you're generating.
Exactly. So a 1 could come from, you got 0.5 and 0.5, or you got 0 and 1, or 1 and 0. But a 2 is less likely because to get something near 2, both of the random numbers need to be close to 1. All right. Now let's try it with 100 uniform random variables. So we're taking the sum of 100 random variables that are all uniform between 0 and 1. Take a minute to predict to yourself what this histogram is going to look like. All right, let's try it. And here we are. So we're again seeing that values in the middle, so near 50, because we added 100 values between 0 and 1, so like 0.5 times 100. Those values are more likely, but now instead of sort of a triangular shape, we have more of a curved shape. And this leads us into an important property about the sum of random variables. So we're going to have 3 properties here. So we're letting x1, x2, up through xn be independent random variables from the same probability distribution. We don't know what distribution, just it's all the same. That has mean, mu, and variance sigma squared. And we'll let y be a new random variable that's equal to the sum of all of the x's. Then 3 things are true. First, the expected value of y is n times mu, and the variance of y is n times sigma squared. That's true no matter what distribution we're coming from. Second, if the x sub i's are normally distributed, then y is also normally distributed. And finally, the property that explains the shape of the histogram we saw is what's known as the central limit theorem. And this says that if the x sub i's have some other distribution, not normal, then the distribution of y will still approach a normal distribution as n approaches infinity. Take a moment to get that in your notes. So our key idea here is that if n is large, then y, defined as the sum of n independent x sub i's, will be approximately normal. Kyle says, I didn't get that last point. You want to see it some more? There it is. So this last point is the theorem that explains what we saw in R. That we started with some other distribution, a uniform distribution in that case, and we took the sum of 100 uniform random variables, and we saw that that histogram was close to being a normal distribution. Cool. This also works for the sample mean, x bar. So same thing, taking the sum of the x sub i's, but just multiplying by 1 over n. This also is approximately normal if n is large. An important question is, how large is large? That depends on how skewed the original distribution is. N greater than or equal to 30 is a common threshold. If you start with a distribution that's symmetric, just not normal, such as a uniform distribution, often less than 30 is fine, like 20. If you start with a distribution that's extremely skewed, you might need to go bigger to get an approximately normal distribution. But in general, greater than or equal to 30 as your sample size is generally a good threshold. Questions about this? Folks online, any questions? All right, so we will see an example of how to use the central limit theorem on Monday, and then we'll talk about the gamma and exponential distributions. I'll see you then.